Scientists built a universe inside a supercomputer, and they expected it to behave like a model. In science language, that part is simple. Simulations do exactly that. You define rules, set starting conditions, and watch behavior emerge. But this story is not a sci-fi scene. It is a science method scene, and method scenes are where serious audiences stay loyal. Scientists built a simulated universe with explicit assumptions. The first stage worked. Then the second stage produced a result that did not sit neatly in the expected distribution. Think of the result as a mismatch between model expectation and generated output. In public-facing science, that mismatch is dangerous territory. It is where excitement and caution have to coexist. If it were a one-off failure, this would be a debugging story. But the team ran the simulation again with different seeds, changed the hardware stack, and adjusted input variance profiles. The results still held. That is the first discipline point. Persistence across variation is interesting, not because it proves mystery, but because it narrows the explanation space. Could it still be a computational artifact? Absolutely. Could it be an implementation bias in data pipelines? Also absolutely. Could it imply a deeper mechanism not captured in the governing assumptions? Also possible, but still a hypothesis. Now, three things are often confused at this stage. First confusion, anomaly versus impossible. Second confusion, unusual versus proven. Third confusion, I can see it versus the numbers support it. If you watch closely, a robust explanation moves from visual intuition to testable evidence. The better way to frame it is, this pattern persisted where our controls said it should not, under these exact constraints. Not, this proves we are living in a simulation. Not, this is the universe fighting back. Just this, our model class may be incomplete. Think of weather models. Most days, they are good enough to route planning and emergency prep. Then a storm arrives with weird micro-conditions and forecasts shift, not always because physics changed, but because your model's simplification hit a boundary. That's the same logic in this simulation story. Maybe the model did the right thing, but in a narrower context than we assumed. In this package, use a small failure before proof beat. Show the first pass failing under a tighter error check. Then show that correction alone does not erase all structured output. The audience trusts a story that admits this because it resembles real inquiry. Now let's separate two audiences, creators and scientists. For creators, this is the reason your next internet rabbit hole is not a trap. It is a roadmap. For scientists, the lesson is not cosmic speculation. It is experimental hygiene at scale. What changed from the initial claim to the final claim? Language. In the first take, this proves we live in a virtual universe. In the second take, this is a reproducible anomaly under defined settings. Both are powerful. Only one is trustworthy. That distinction is your credibility asset. When you present this correctly, the story becomes bigger than one headline topic. It becomes a template for how people should consume fast science claims online. Because the internet rewards hype, but science rewards correction. Keep that tension alive, and the video naturally stretches to 8 minutes or more. If this anomaly is real in the strictest technical sense, it becomes a signal to redesign the prior architecture. If it turns out to be an artifact, it still becomes a signal to redesign instrumentation and trust boundaries. Either outcome is useful. That is why this is a high-value science narrative despite the uncertainty. So no, this is not a confirmation of simulation reality. But yes, this is a reminder that our synthetic worlds can reveal where our scientific thinking is too tidy. If you build models, here is your takeaway. Test for surprise, then resist the temptation to announce a grand conclusion. If the anomaly stays, keep testing. If it fades, keep learning. In both cases, progress looks the same. Less certainty, better method, stronger signal discipline. That is how science stays alive long enough to be trusted. And sometimes, the most powerful discoveries start with a question nobody wants to answer the first time. Maybe the world is not in a computer. The bigger question is whether we already know how to